Alright, so today I'm going to be explaining a very important paper by Google Brain and Stanford University, which is highly cited. This paper is score-based generative modeling through STE, stochastic differential equations. This ICLEAR paper in 2021 that you see many, even today, you see many papers are citing this paper because it's very important. Creating noise from data is easy. Creating data from noise is generative modeling. We present a SDE that smoothly transforms a complex data distribution to a known prior distribution by slowly injecting noise and a corresponding reverse time STE that transforms the prior distribution back into the data distribution by slowly removing the noise. Crucially, the reverse time STE depends only on the time-dependent gradient fields, for example, the score of the perturbed data distribution. By leveraging advances in score-based generative modeling, we can accurately estimate these scores with neural networks and use numerical SDE solvers to generate samples. Because of these numerical SDE solvers, still we use graph autoencoders instead of these methods for big graphs, because for large graphs the computational complexity is huge. So if the graph is moderate or small in size, then these ideas like this paper is very good. So let's carry on. We show that this framework encapsulates previous approaches in score-based generative modeling and diffusion probabilistic modeling, allowing for new sampling procedure and new modeling capabilities. We introduce a predictor-corrector framework to correct errors in the evolution of discretized reverse time STE. Because we don't learn the forward, we just learn the reverse process. So we need to learn, and we also derive an equivalent neural ODE that samples from the same distribution as the STE, but additionally enables exact likelihood computation. This is important. If your likelihood is exact, you can do it. And improved sample efficiency. If you compare graph autoencoder with this method, we can say that this method is exact, unlike the previous paradigms. And you see this, we solve a reverse time STE yields a score base. This gradient of the log of probability, we call it a score function in machine learning. And transforming data to a simple noise distribution can be accomplished with a continuous time STE. So this STE can be reversed if we know the score of distribution. If you don't know the score, then you should learn it. You should learn it with neural networks. The neural network learns this score. So flexible sampling and likelihood estimation. Controllable generation. We can modulate generation process by conditioning on information not available during training. Because the conditional reverse time STE can be efficiently estimated from unconditional scores. The background that you need is this: that we want to train a noise conditional score network. We call it S. So we are learning this S with a weighted sum of denoising score matching. Oh, by the way, we call this paradigm score matching. It's not new, it's very old idea. But the way that we are working with that is interesting because we are using STE now for the reverse. We are learning it. So it's very interesting to learn the parameters of theta so that S theta could be a very well approximation of your real gradient of log p. So the optimal score base S theta star matches this. If it is optimal, then this is very, very near this amount. So for sampling, this reference run m steps of Langevin Monte Carlo MCMC to get Markov chain Monte Carlo to get a sample for each p. Because we need to sample it, so we can easily use Langevin MCMC. Because once you learn S, then you can sample it very easily. And the other thing you need to know about elbow that you are familiar with. So it's a reweighted variant of elbow that, as I said, we are learning this S from this data. After solving it to get the optimal S theta star, samples can be generated starting from Markov chain. Okay. So what is score-based generative modeling with SDE? Our goal is to construct a diffusion process indexed by continuous time variable t, such that your initial value is p0, which we have a data set of IID samples, and also your target, your final X could be anything, image, graph, anything, language. So we have a tractable form to generate samples efficiently. In other words, P star is a data distribution, and the PT is the prior distribution. This diffusion process can be modeled as solution to Ito. By the way, this Ito is a Japanese Ito SDE. You know, in financial mathematics, they teach Brownian motion. And for the most important thing is that for any SDE, there exists a linear PDE. And for any linear PDE, you have an equivalent SDE. Of course, nowadays, there are some nonlinear PDE equivalent of that, but mostly we do it for linear PDEs. For linear PDE, there is an equivalence. And Ito is a solution of SDE, and there are many theorems about that we don't need this here. So you see the forward, you go to x sub t, then again from x sub t, you go backward, you reverse, you get your data. Because you are learning this gradient of log of p. So as I said, probability flow ODE can be obtained by the score of gradient of log p. So we map data to the noise distribution, which we call it prior. So by storing the samples and reversing the process, we can obtain samples. A remarkable result states that the reverse of a diffusion process is also a diffusion process. Now, the important part of this paper is here, estimating scores for the SD. The score of a distribution can be estimated by training a score-based model on samples with score matching. To estimate this gradient of log of P, we can train a time-dependent score-based model. So it's just a continuous generalization of equation 1 and 3. So your expectation is over x theta, xt, x initial, your prior, and this is how you can estimate theta that we need for this score function. So the noise perturbation used in SMLD and DDPM can be regarded as discretization of two different SDs. When using a total of n noise scales, each perturbation kernel of SMLD correspond to distribution of X sub I. So this was an example, and then we propose a new type of STE which perform particularly well on likelihood given by this. So when using beta, this beta you see, and starting from same initial distribution, the variance of a stochastic process induced by this equation is always bounded by the VP STE at every intermediate time step. So solving the reverse STE after training a time-dependent score-based STE, after learning STT, now we can just use a reverse time STE. And then simulate it with numerical approaches to generate the samples from P0. So it says this table shows comparing different reverse time STE solvers on CFAR10. Shaded regions are obtained with the same computation. And this is another contribution of this paper, that predictor corrector samples. Unlike generic STEs, we have additional information that can be used to improve solutions. Since we have a score-based model, we can employ score-based Markov chain Monte Carlo approaches such as Langevin MCMC. So the numerical STE solver first gives an estimate of the sample at the next time step, playing the role of a predictor. Then the score-based MCMC approach corrects the marginal distribution of the estimated sample, playing the role of a corrector. So the predictor is the numerical STE solver. So the score-based MCMC approach corrects the marginal distribution of the estimate sample, playing the role of a corrector. This idea is analogous to predictor corrector methods, a family of numerical continuation techniques for solving systems of equations. So you see in Table 2, NLLs and FIDs, ODE on CFAR10. You compare different models, very popular models like DDPM. And here they talk about exact likelihood computation. As I said, it's very important. Leveraging connection to neural ODE, we can compute the density. Here we can compute the density via the instantaneous change of variable formula. This allows us to compute exact likelihood on any input data. So we report the negative likelihood measures in bits per dimension on the CFAR10 dataset. Unlike most current invertible models, our encoding is uniquely identifiable, meaning that with sufficient training data, model capacity, and optimization accuracy, the encoding for an input is uniquely determined by the data distribution. So as we can sample X0 from P0 from different final conditions, you get this probability flow ODE that enables fast sampling with adaptive step sizes as a numerical precision. You know, this is very simple for images that look like it's very continuous variable. But for graphs and language, because they are combinatorial, you need to do more work. There are many details that you need to know. But for images, everything is easy. All problems are easy. And the conclusion. While our proposed sampling approaches improve results and enable more efficient sampling, they still remain slower at sampling than GANs. This is an important remark. Still slower at sampling than these traditional GANs.